In today's class, we are going to discuss about magnetism and matter. Here, the first topic what we are going to discuss is about magnetic movement. Magnetic movement. So here we have to know about what is magnetic movement and for a given magnet. For a given magnet. I have taken one bar magnet means every magnet will have two poles. This is one bar magnet. It is having two poles. One is south pole, other one is north pole. So these are the two poles of the magnet. Always the poles will lie just before the ends. The concentration of the strength will be just before the ends. We call them as poles here. Poles. Here the poles, here this is a one pole is south pole, one pole is north pole. Like that we categorize here. So if you observe a magnet, it has two poles separated by some distance. Let me take the distance as distance from south pole to north pole as 2L. 2L is the distance from south pole to north pole. And here we are using the term capital M. Capital M is called as magnetic movement. Capital M is called as magnetic movement. And here we observe two poles lies exactly at the end, not completely at the end, just before the ends. Just before the ends, two poles are located. Both are having opposite nature. One is south pole, other one is north pole. So the strength of the pole is given by small m. Small m is called as pole strength. Pole m is called as pole strength. And distance between south pole and north pole, we can call it as 2L. The 2L I taken. Sir, is there necessary to take 2L? Can we take L? Means yes, you can take L also. Then why you are taking 2L here for length of the magnet? It means the reason is this 2L. If you take when you are doing some derivations, it will become very simple beta. Just for further derivations, what we are doing, we don't get complex expressions if you take 2L. Even you take L also no problem, but 2L will get less complex expressions. So here that is the 2L is called as magnetic length. 2L is called as magnetic length. And small m is pole strength. Here we have two poles, south pole and north pole. Both have same strength. Both will have same strength, that is equal to small m. Small m is pole strength. And this is called as a bar magnet. I am taking one bar magnet. So here one important point to be noted is whenever you take a bar magnet, the end from one end to other end is called as geometrical length. Geometrical length from one end to other end. And here from south pole and one more is north pole. The distance between south pole and north pole is called magnetic length. Magnetic length. So here if you observe, what is the relation between magnetic length and geometric length means, I can say magnetic length is 5/6 of geometric length. There is a difference for magnetic length and geometric length. Here ML is called as magnetic length. GL is called as geometric length. So what is the difference between them? Why we got two lengths for a magnet means one is geometrical length. Geometric length means from one end to other end. From one end of the magnet to other end, completely from one end to other end is called geometric length. The problem is the poles are not existing at completely at the ends of the magnet. They lie just before the ends. Just before the ends. There are two poles, south pole, north pole. They are non-identical. One is south will be there, one is north will be there just before the ends. They are not completely at the ends. So the length between south pole to north pole is called as magnetic length. Length between south pole to north pole is called magnetic length. How magnetic length is connected with geometric length means Magnetic length is equal to 5/6 of geometric length. Magnetic length equal to 5/6 of geometric length. Here, coming to here, now what we are discussing here, 2L is nothing but magnetic length, not geometric length, beta. 2L is called magnetic length. Here we have taken. Magnetic length means length between where to where, that is south pole to north pole of the magnet. The problem is they are not lying completely at the ends, just before the ends of either side. So length between south pole to north pole is called magnetic length. From one end of the magnet to other end geometrically, that is called geometric length. How they are related? Magnetic length is 5/6 of geometric length. Mathematically, what we can write here? Magnetic length, I can also write it as 83.33% of geometric length. Here we can write the relation for magnetic length on geometric length like this also, beta. In terms of percentages, magnetic length will be 83.33% of geometric length. I hope you got information about magnetic length and geometric length and you got clarity in that. Now let us observe here the magnetic length and geometric length relation we observed. Now what is magnetic movement? We have to know about magnetic movement. Capital M is called magnetic movement. It is a vector quantity, small m into 2L bar. This 2L bar is called magnetic length. 2L bar is called magnetic length. And capital M is called capital M bar, magnetic movement. It is a vector quantity. It is a vector quantity. And its SI unit. What is SI unit of magnetic movement means? I can write ampere meter square. For pole strength, ampere meter. For magnetic length, meter. These are SI units. The SI unit for pole strength is ampere meter. And for length, you know, length SI unit means meter. And for magnetic movement it is ampere meter square. Ampere meter square. Let us check the detail about magnetic movement now. Here we told that if we have observed any magnet, this is a bar magnet, I'm calling it as, we have two poles, south pole and north pole, and length between south pole to north pole is called as magnetic length. Magnetic length. Here each one is having the two poles. Each one is having strength small m. Small m is called as pole strength. Small m is called as pole strength, I told. And 2L is, I have to write 2L bar, is magnetic length, I told. Magnetic length is vector quantity. Vector quantity. Vector means direction is required. What is the direction here? Direction is south pole to north pole. Direction is always south pole to north pole. So we are taking magnetic length means magnetic length is measured from south pole to north pole. South pole to north pole. As direction is from south pole to north pole, now magnetic movement capital M bar is equal to small m into 2L bar we have written. The direction of magnetic movement also, the magnetic movement direction is also from where to where. From where to where means we have to write from south pole to north pole. South pole to north pole. Observe carefully here. Here 2L bar, south to north. Magnetic movement small m into 2L bar, small m scalar, 2L is vector. So m bar direction, 2L bar direction same. So south pole to north pole, magnetic movement direction. This is the information about direction of magnetic movement. Capital M, you know it as magnetic movement. Magnetic movement. Every magnet has a characteristic that is a magnetic movement by which we decide is a strong magnet or a weak magnet. If strength is the magnetic movement is more, it's a strong magnet. Less, weak magnet. So I hope you understood about what is pole strength. Poles always does not exist completely and ends, they will exist just before the ends. 2L magnetic length, direction south to north. And magnetic movement also directed from south to north. Magnetic movement vector quantity and pole strength SI unit. Already I have written pole strength SI unit is ampere meter. Magnetic movement SI unit is ampere meter square. Ampere meter square. Like that, I can write the information here. I hope you are clear with what is magnetic movement. What is magnetic movement? Now, let us enter here. If some applications we are going to observe now. So there is one magnet, they kept like this. Magnet has south pole and north pole. And what is the direction of magnetic movement? Magnetic movement direction is from south pole to north pole. Magnetic movement direction is from south pole to north pole. And its value is M1. And I am taking another magnet. This magnetic movement, there are two different magnets. What is the magnetic movement direction for any magnet? Magnetic movement direction is from south pole to north pole. Here these are two non-identical magnets. Non-identical magnets, if they arrange like that, what is the net magnetic movement? They combine like that. What is the net magnetic movement? Net magnetic movement, simply we can write M1 plus M2. Suppose they have given that in one application, here they told, and one more, before going to next application, here we'll say one point here, that is, if the magnetic moments are equal, if M1 is equal to M2 is equal to M, let us say M1 is equal to M2 equal to M. So what will happen to the net magnetic moment here? Net magnetic moment is equal to M plus M. It is 2M. M plus M, 2M. So this is the net magnetic moment. If at all, if they are equal, we can write in this way. So now let us observe another condition. I hope you are clear with this application. Now let us see the next application. They are telling that now one magnet, okay, they arrange it like this. And another magnet, what they did here is, they are taking the south pole and north pole in reverse direction. So they kept south pole here, north pole here. Now we know that direction of magnetic movement is south to north. Direction of magnetic movement south to north. So here this is M2. Let us take here both are what happened opposite. As both are opposite here, we must not take positive sign. We have to take difference. So which is greater value minus small value? Which among them greater minus small? We must not get negative sign. So always take great value minus small value. You will get the net magnetic moment. So here opposite directions, because magnetic movement is directed from where to where? South to north, south to north. Both are opposite if they arrange it like that. So what will happen to the net magnetic movement in these directions means net magnetic movement both are equal M minus M. M minus M means 0. Net magnetic movement is 0 if you arrange in this way. I hope it is clear now. Let us see next one here. So here what they are telling now, they are telling that if I have taken one magnet like this, south pole, north pole, they arrange another magnet in this way, south pole, north pole. So here this is the first magnet and this is the second magnet. So direction of magnetic movement is always from where to where? South pole to north pole, M1, south pole to north pole, M2. What is net magnetic movement? Both we observed in same direction, net magnetic movement again M1 plus M2. Suppose we observe that if M1 and M2 are equal to M, if M1 and M2 are equal to M, then what we can write? M net is equal to 2M. So if the arrangement is like that also, we'll get the net magnetic movement in this way. I hope you are clear. Very simple application. Magnetic movement direction we observed. and from that both are same direction, we are adding and we got this information. So we are comfortable till here. Suppose they told that in this second magnet, they have arranged here north, here south. Now what is the direction of magnetic movement? Magnetic movement from south to north. Both are opposite. Both are opposite means what will get here? M naught is equal to M1 difference M2. M naught value is, when if they are equal, what is M naught value? M naught value is 0. M naught value is 0. Like that we can write. Now let us see one more application. One more application now. So now if the two magnets are arranged like this, or two magnets are arranged in this way, or the two magnets are arranged like this. In all these cases, observe, anyway you take south, north, wherever you want to take these poles, that is a south, north, anywhere you take, that is either left to right or right to left, you change, nothing will happen. South to north, here south to north, here south to north. Now what is the direction of magnetic movement in any situation? Here magnetic movement is always directed from south to north. Magnetic movement is always directed from south to north. So for this magnet M1, for this magnet M2. So here observe, magnetic movement south to north. Magnetic movement south to north. For this magnetic movement M1, for this one M2. Magnetic movement directed from south to north. Magnetic movement directed from south to north. Observe, in all cases, these are perpendicular. Those are M1 and M2. If you observe, they are perpendicular to each other. They are perpendicular to each other in all the cases. In all the cases, M1 and M2 are perpendicular. Perpendicular means what is the net magnetic moment? Net magnetic moment we can write now, square root of M1 square plus M2 square. Square root of M1 square plus M2 square. If suppose M1 is equal to M2 is equal to M, then what will happen? M1 is equal to M2 is equal to M means net magnetic moment is equal to, we'll get root 2M, root 2 into M, root 2 into M. Just substitute in the place of M1 M, M2 M. Square root of M square plus M square, square root of 2M square. Square root of 2M square means root 2M, root 2M. So whenever we observe, they are perpendicular, magnetic moments are perpendicular, this is fixed. Magnetic moments are perpendicular. The values what we get, M naught is square root of M1 square plus M2 square. Also M naught is root 2M. Next. Here, actually we have one parallelogram law of vector addition long back. If you observe, this is a vector P bar, this is a vector Q bar. Then the angle between them is theta, means R is equal to square root of P square plus Q square plus 2PQ cos theta. R is the resultant of P bar and Q bar. R bar is resultant of P bar and Q bar. This is information from parallelogram law of vector addition, which is there in motion in plane chapter. Parallelogram law of vector addition. This is there in motion in plane chapter in +1 syllabus. Now our target is not this one. Our target is that there are two magnets. So this is one magnet, another magnet, like that. They are inclined with an angle here. South pole, north pole. South pole, north pole. So what is the direction of magnetic movements? Direction of magnetic movement south to north, M1. Direction of magnetic movement south to north, M2. So angle between these two is theta. Now M1 and M2 are the magnetic movements inclined with an angle theta. What is the resultant magnetic movement? resultant magnetic moment, here we can write m net is equal to square root of m1 square plus m2 square plus 2m1 m2 cos theta. 2m1 m2 cos theta. This is the resultant magnetic moment when m1 and m2 are inclined with an angle theta. I hope you are understanding how to write. This is from parallelogram law of acceleration, net magnetic moment. Here, suppose what is the main condition you observe? Like poles in contact. We made in a such a way that we arranged to keep the like poles contact, like poles contact. So like poles we kept in contact. This is the situation. So when like poles are in contact, the net magnetic moment, what is the formula for net magnetic moment means? Square root of m1 square plus m2 square plus 2m1 m2 cos theta. If theta is equal to 0 degree, if theta is equal to 0 degree, what will happen to the net magnetic moment? Net magnetic moment will become 0 means cos 0 1, cos 0 value is 1, cos 0 value 1 means you'll get square root of a square plus b square plus 2ab. So we'll get here magnetic moment as, what will get better magnetic moment, will get it as m1 plus m2. Because cos 0 1 square root of a square plus b square plus 2ab means square root of a plus b whole square. Square root of a plus b whole square is a plus b. From that information I can write m1 plus m2. Suppose if theta is equal to 180, theta equal to 180, then what will happen to the net magnetic moment? Net magnetic moment cos 180 minus 1. Cos 180 minus 1 means square root of m1 square plus m2 square minus 2 m1 m2 cos theta. We'll get the expression as m1 difference m2, m1 difference m2. If suppose if theta equal to 90, cos 90 0, cos 90 0, this term 0 means this total will become 0. So we are left with net magnetic moment as square root of m1 square plus m2 square, square root of m1 square plus m2 square. This is the situation when we are observing when like poles are in contact, like poles contact. We arrange in such a way that like poles are placed at one point. This is the situation. Next, let us observe here. Just now we noticed, note point will observe m magnetic moment is m net is equal to, I wrote it as square root of m1 square plus m2 square plus 2m1 m2 cos theta I have written. If at all m1 and m2 are equal to, m1 and m2 are equal to m, let us say they are equal to m, then what will happen to the expression? So what will get here? M net is equal to square root of m square plus 2m square cos theta. So m net is equal to square root of m square plus m square is 2m square plus 2m square cos theta. So here m net is equal to, if I take 2m square common, 1 plus cos theta. Here you observe here 2m square I have taken common here. First m square plus m square 2m square, again 2m square common, will get into 1 plus cos theta. Let us take the next page here. Here what happened? M net is equal to, now what should I write? So we got in previous, we have written it as 2m square into 1 plus cos theta. We know from our maths, magnetic moment now, 2m square into 1 plus cos theta can be written as 2 cos square theta by 2. 2 cos square theta by 2. 1 plus cos theta can be written as 2 cos square theta by 2. This is the value for 1 plus cos theta. Trigonometry identity says like that. So now what is the expression for m net? So finally we got m net as 2m cos theta by 2. 2m cos theta by 2. This is the expression for net magnetic moment. 2m cos theta by 2. This expression when if m1 and m2 are equal, m1 and m2 are equal and like poles touch, like poles touch, making an angle theta, m1, m2 are equal, m net is 2m cos theta by 2. Now, let us observe carefully 3 points here. Now we are going to observe 3 points. Pay complete attention beta here. The important 3 points I am going to discuss now. Here, first case, if theta is equal to 60 degree. So here theta 60 means here theta 60 by 2 30 cos 30 is root 3 by 2. So 2 will be cancelled and we can write m net as root 3m root 3 into m. Suppose now if theta is equal to 90 degree, theta is 90 degree. Observe now, here what I am doing here, theta equal to 90, I substitute here 90 by 2, 45, cos 45, 1 by root 2, cos 45, 1 by root 2, 2 by root 2 is root 2. So I can write m net is equal to root 2m, m net equal to root 2m. Next you observe, if theta is equal to 120 degree, 120, so theta is 120 cos 120 by 2 cos 60. So cos 60 1 by 2, 2 cancel. So what we get here, m net value simply m. So we have to remember whenever like poles touch all these points. So like poles touch means what we discussed. First, this is the situation like poles touch, south pole touch, or north pole touch. So your angle between the two magnets is theta. Then from parallelogram law of vectorization, if two vectors inclined with an angle theta, this is the formula. Theta 0 as substituted, we got maximum here, maximum. Theta 180, minimum. Theta 90, like that. This is the maximum value. We can also write here. This is the maximum value, maximum. Here this value I can also write minimum value. Theta 180 minimum, theta 0 maximum. Theta 90, by substituting that values we got these expressions. After that, what we discussed here, we told that you have taken m1 and m2 values are equal, m1 and m2 values both are equal means finally by just simplification substituting here and what I did, I simplified and I got the expression as 2m into cos theta by 2, 2m into cos theta by 2. When m1 and m2 are equal, net magnetic moment is 2m cos theta by 2. Here theta is 60, net magnetic moment is root 3m. Theta is 60, net magnetic moment is root 3m. Theta equal to 90, net magnetic moment root 2m. Theta equal to 120, net magnetic moment is m. Like that we got the expressions here. I hope this is clear. Now let us observe what is the situation when unlike poles are in contact. Our target is now unlike poles in contact. Like poles in contact over. Now our target is unlike poles. So let us observe what is the situation when unlike poles are kept in contact. Unlike poles kept contact. Let us observe carefully that one. Here one magnet is there. This is the magnet, south pole, north pole. And here unlike pole means what you are right, north and south. Now here magnetic movement is always directed from where to where? South to north and south to north. Magnetic movement direction is from south to north. Here also we can write magnetic movement direction from south to north. So this direction I can write it as M1. Magnetic moment for that one is M1, M2. Here angle between the magnets is theta. Remember carefully here, angle between magnets is theta, not magnetic movements. Angle between what is magnetic movements? I can write this as now 180 minus theta, 180 minus theta. So what we can write here, net magnetic moment here, angle between the two magnets is not theta. Here when unlike poles contact, what we can write? The angle between the two magnets is 180 minus theta. That means here observe carefully, m net is equal to square root of m1 square plus m2 square plus 2m1 m2 cos 180 minus theta, cos 180 minus theta. Angle between them is cos 180 minus theta. What we got beta? Cos 180 minus theta. Cos 180 minus theta is minus cos theta. Cos 180 minus theta is minus cos theta. So as cos 180 minus theta, observe carefully here. What is cos 180 minus theta? Minus cos theta. So I got here minus sign, minus sign. If here this is a minus sign, now the expression when unlike poles contact each other means m naught is square root of m1 square plus m2 square minus 2m1 m2 cos theta. Observe carefully here. Theta 0, theta 0. Theta is 0 means net magnetic moment. What is net magnetic moment here? M1 plus M2 we can't write because here theta 0, cos 0, 1. We'll get minus sign here. So here now we have to change these things. So here what will happen? Theta is equal to 0 will get negative sign. When theta is 180, what will happen? You will get positive sign because cos 180 minus 1. Cos 180 minus 1, minus of minus plus cos 180 minus 1. So now we are reverse. When we are getting minimum, when we are getting maximum now, theta is equal to 0. We are getting minimum value. Theta is 0 minimum. Theta equal to 180 maximum value. Reverse from previous condition to here. But this is same. Last one theta 90, cos 90 0. This total is 0. So last theta equal to 90 condition is not affected. Theta equal to 90 condition is not affected. So I hope this is clear to you now. Let us observe net magnetic moment. What's the formula here? M1 square plus M2 square. What I have written? Minus 2M1 M2 cos theta. Here again same everything. Just remove the plus sign. Remove the plus sign. Instead of plus sign, what you have to substitute? Minus sign. Minus sign. Minus sign. So what is 1 minus cos theta? What is 1 minus cos theta? You have to know. So 1 minus cos theta. 1 minus cos theta is nothing but 2 sine square theta by 2. 1 minus cos theta is 2 sine square theta by 2. Remember 1 plus cos theta, 2 cos square theta by 2. 1 minus cos theta, 2 sine square theta by 2. From trigonometry, we have those expressions. Now 1 minus cos theta, 2 sine square theta by 2. So if you remove those terms here, now what will happen here also? What will get now? 2m sine theta by 2. 2m sine theta by 2. Here what poles are in contact? Unlike poles touch. Unlike poles touch. Now here what will happen now? Again you observe carefully here the values here. Again these values will change. Observe carefully what are the changes here. Here sine theta by 2. First theta 60. Theta 60 I am taking. Theta 60 means sine 60 by 2. Sine 30. Sine 30 1 by 2. 2 to cancel. And m net value is m net value is m. M net value is m. And now again observe here theta is 120. Theta 120 sine 120 by 2 sine 60. Sine 60 root 3 by 2. 2 to cancel. So we'll get here what we are going to get. root 3m. But this is not affected. This is same. Why? So here sine 90 by 2, sine 45, sine 45, 1 by root 2, 2 by root 2 is again root 2m. So I hope you understood how to handle these situations. Net magnetic movement in different conditions, Now, let us observe here one more point here. So now we got the conditions when like poles touch, unlike poles touch, all the things are clear. Let us observe. Here a straight magnet is there. Let me take it, this is south pole and this is north pole. Now this is now cut, they made into the shape like this. This is the made into shape like this. This is south pole and this is north pole. So now what is a magnetic movement? Magnetic movement, let us take here, it is M. Magnetic movement is always, so south pole to north pole distance is 2L and pole strength of each one is small m. So capital M is small m into 2L we have. In this case, if this magnet is bent in the shape like this, so what is the new magnetic movement? What is the new magnetic movement? M dash is equal to, now the magnetic moment of this one is M dash. First of all, magnetic moment. What's the magnetic moment? Pole strength into magnetic length. Pole strength into magnetic length. If this magnet is bent like that, pole strength is not affected. Pole strength is not affected. So pole strength will remain same. Pole strength will remain same as small m. But what about magnetic length? Magnetic length. Here from here to here it is 2L. Now it is divided for 3 equal parts, means I can write this part is having 2L by 3. This part is having 2L by 3. This part is 2L by 3. So now what is the shortest distance between south pole to north pole? From here to here, if you observe, this is also 2L by 3. This is also 2L by 3. So magnetic length is a vector quantity. Magnetic length is a vector quantity. Always straight line between south to north pole. Now even you bent like that, it must be straight line between south to north pole. Straight line between south to north pole. What is the information we got? 2L by 3. 2L by 3. Because this is 2L by 3. This is also 2L by 3. So now what should I write? M dash is equal to M into 2L by 3. Actually, we have written that small m into 2L as what? Capital M. So from here, what is M dash? M dash is equal to M by 3. M dash is equal to M by 3. Remember, magnetic length is a vector quantity. Magnetic length is a vector quantity. Whenever you take any vector quantity, it is always straight line drawn from south pole to north pole. Straight line drawn from south pole to north pole. Vector quantity must be in straight line only. So here also, this is south pole, this is north pole. Now straight line means actual total length is 2L, 3 parts, 2L by 3, 2L by 3 equal parts. Is a bent into U shape. This concept is called straight magnet, bent into what shape? U shape, U shape. So bent into U shape, then this is the situation what we observed. I hope you are clear with these ideas, beta. This again in next class we will discuss some more points related to the magnetic movement, and how the applications are there. All the things we will discuss in our next class. I hope till here all the students are comfortable and you understood today's topic.